Hello everybody, and in this video I'm going to show the whole process of designing a spare gear and also doing the math and also doing the design in SolidWorks in this example. And in the end you should have a pretty accurate representation of the gear. And about gear analogy, as you know that the involute is like you hold a string and then you pull it upwards and it creates this profile of the involute. Actually, I did research about this topic and I mentioned Spur internal and helical gear using SolidWorks and CATIA depending on the gear, but in Spur gears we use SolidWorks, it's easier. And in this research I explained the whole process, and today I'm going to summarize it or maybe simplify it by explaining it in a video. So first of all, here's a Excel template that I created for the research and I will use it to explain in this video. We're gonna take an example of a spare gear with these, like this given information. It should always be given. Pressure angle, we're gonna choose it to be 20. Pressure angle, you have to make it radians. Excel always deals in radians. We have the module 4mm. Teeth are 16. These are module teeth. Diametral pitch is calculated from the given information. Pitch diameter is the number of teeth multiplied by the module. So this template I will hopefully remember to link it in the description so can easily help you guys. What you have to do is just fill out all the information and follow my steps. Pitch of the diameter. As you know, pitch is here. This is the drawing that I drew. Here's the pitch circle, pitch radius. Here is also another representation pitch circle. I apologize for the quality. This is I'm screen recording on my computer. So pitch of the teeth is equal to pi multiplied by module. Sorry, I was talking about pitch circle before. I apologize. So pi multiplied by the module. Here we have the pitch of the teeth. Circular tooth thickness measured on pitch radius is here's the equation. Pitch of the teeth, I think I don't know how I forgot. I think it's the distance between the beginning of a tooth and the end of another tooth, like similar to the circular tooth thickness. As you know, addendum is equal to the module and dedendum is equal to 1.25 multiplied by the module. Radius of pitch circle is equal to teeth multiplied by module by 2. Teeth multiplied by module gives you the diameter, so just basic math. That's why we divided by 2 to give us the radius. Radius of outer circle, as you know, we have outer addendum, radius, pitch, and dedendum. But the most important is another one is called the base circle, which is sometimes below the dedendum, sometimes it's above. When it's below that, just use the dedendum as a reference. Of course, this video I am treating you as already knowledgeable and in gears, so I'm just gonna explain the process here. Radius of the outer circle, as you know, just equal to the pitch plus the addendum. But the dedendum is equal to the pitch minus the dedendum. It's a funny word actually, addendum, didendum. It's weird. Radius of the base circle, this is important, is equal to the pitch multiplied by the cosine. So here is the pitch multiplied by the cosine of the pressure angle in radian. Here it is. As you can see here, it's between the dedendum and the pitch, so yeah, we can use it as a reference. In terms of why is this role, it's like it goes back to the theory. You can read about this later, but yeah, this is a derived equation. Here it is. Yes. It's yeah, depends on the theory. Radius of the root concave corner. It is 0.38 multiplied by the module. Of course, these equations you can find in the machine design book. I think it was called Mechanical Engineering Design by Bodinas and Nisbet in SI units. Yeah, I'm sorry, but in British units it's different. We do not, in British units they don't deal with module, they deal with I think diametral pitch. So yeah, I'm treating this video only SI units. Hole depth, yeah, from top to bottom is addendum plus dedendum. Circular pitch, yeah, we don't, it's, why do we need all this? Just to make sure when the final product is up, we want to make sure is our calculations was correct or not. Because usually we reverse engineer a gear by designing it here, so at the end we have to compare it with the actual product. Pi divided by the diametral pitch. Circular pitch divided by 2. Clearance is here, clear circle is dedendum minus addendum 1. P angle. P angle is for the pitch circle angle. Cosine inverse equals root circle divided by outer circle. Here's the root circle divided by outer circle. Inverse of P angle, as you can see, tan the P minus P. Sweep parameter, it's you can choose it. It's I choose it to be in the middle. It depends on your selection. By coordinates of the involute tooth profile, which means the base circle. The base circle. I want to know the coordinates of the point B here. Since we know the radius, it's equal to base radius. Where was it? Actually forgot where it was. D17. Oh, sorry. The base radius right here. I apologize for that. Multiplied by sine sweep multiplied by pi, and usually the sweep is 0.5, yeah, minus cos sweep as well multiplied by pi multiplied by sweep multiplied by pi. Yeah, something wrong here. But yeah, I did not invent this equation. Of course, I took it from the book, but it works. And this method that I made a publication of is actually a novel method that has not been done before. And I compared it with already existing research, and it appeared to be the most accurate one. Thank God. So yeah, this is good news. Pi. Yeah, this template is very important. Just follow the equations here. Now, this is the most important information because they govern the, like, our aim is to create this profile, this shape here. It's like a V, closed profile V. Then extrude it in SolidWorks to make the gear. The addendum. It's the pitch plus addendum. Now, pitch, as we already know it, 32. Base, it's right here. I'm just filtering out all this information. The addendum, where was it? Pitch minus the addendum. Okay, clearance is not important right now. So this is my research is focused about this. FOC. This equals the distance between the tooth, which is the circular pitch divided by 2, and we already got it here. Circular pitch divided by 2. What was it? Yeah, here, tooth thickness. The thickness in the pitch radius, the thickness between of the tooth is the same as the distance between each teeth. So we will use this information, and this is the most important part in my research, is to use this information. So 360, because it's a circle, divided by 2 multiplied by number of teeth. It's up there, but I know it's 16, but just to be simple, 11.25. Okay, this angle, I want to make it in radians. So pi divided by 180. Good. And since the FOC is this, I want to divide it by 2 to get the HOC. Here, the angle HOC. The angle HOC in radians is, because Excel only deals with radians, that's why. Yeah, is this correct? I think there's something wrong. Yeah, I think this should be this actually. Yeah, because I already turned it to radians, then I calculated it again, so that's what was my mistake. Now, the coordinates of the point C, which is right here. It's important. Why? Because to check, since we will begin from the base and sorry, and reach the addendum, that's why these are the the pitch circle is in the middle, so we use it just to check our formation. I apologize for the sore throat. Pitch circle, what was it, multiplied by sine angle HOC in radians is equal to 3.13. Correct. Pitch and the cosine, because as you can see, the angle is right here, So with cosine it gives us the y coordinates here, but with sine it gives us the x coordinate. As you can see, the y coordinate should be really high and the x coordinate should be not so much. As you can see, the x coordinate at 3.13, so it depends on this value, like how much is it. So let's check. Pitch 32 multiplied by cos angle. See, the difference is huge. The coordinates of point A, the dedendum. We treat the distance between A and B, the dedendum and the base circle, to be a straight line, so the angle is similar. And this is like assumption. Yeah, this is my assumption. Oh, sorry, it was already here. Like I could just take from here. Multiplied by sine angle HOB, which is I forgot about that. Yeah, give me just 1 second. The angle of the base circle. We have to first calculate it from here. So let's calculate it. PQ. What's up with this is that here, let me show you. There's a picture here. Yeah, as I told you, that a string fixed at some point and being pulled by us will create the involute shape. So this is the novel idea of the research, is that at first it is at point B, and then it creates the involute profile. And as we can see, the angle here, which the straight line goes to the B, keeps changing. So here's the point B, PQ. PQ is the length here. It should be fixed. Yeah, I'm gonna leave this, not because I forgot it, of course. It's just because to not waste any more time, but I will link this in the description so you can read my paper and yeah, give me views on it. I apologize for long time of this video. So square root pitch circle, there's my power of 2 minus base circle power of 2. Yep, it's correct. PQ divided by base circle. Correct. This will make a lot more sense when you read the paper. Base circle divided by pitch. The angle sum minus rod, and the end is the angle HOC. I'm sorry, this one. Radians divided by this. This is the most important thing, the base circle. Yes. So back to the dedendum. It equals to dedendum multiplied by sine angle HOB. Correct. I'm sorry. Dedendum multiplied by cos angle. Yes. Now that we know where we're gonna start from, which is the base circle, and we know the difference in angles, as you can see, when we move, the angle is changing here, this angle, so it's constantly going to change, and we have to constantly get the coordinates of the xy coordinates of the involute, and this is in this template. As you can see, I'm gonna calculate the distance PQ. Like this, I did this for the point, and now I'm gonna do it for each point on the involute. Radius, distance, the angles, and finally this is the most important angle. Then I will get the coordinates of the involute at first, then I'll explain the rest. So where do we begin? The base circle, as we know, starts from base radius 30.07, and now I'm gonna make an increment, and how low the difference is how accurate or how more quality is the line, but it does not affect too much. I'm going to choose my increment increment as 0.2. See, 30.1 and here 30.2, and you 30.3, and you're gonna ask me till when? Till the addendum, which is 36. So what you do like this and keep increment till you see 36.1. Just make it 36. Yes, should be it. And now I'm gonna calculate the PQ for each individual point. Square root is equal to the radius power of 2 minus base circle divided by power of 2. What's this? 0. Yeah, I think I made a mistake. 5. No, actually there's no mistake. I think it's correct. Yeah, the thing is that this is exact point, so I'm just gonna make it not so exact, because it's 30.07, sorry, point something, so make it accurate. Yeah, 3.0. I hope you understood that. And the basic does not change, but the radius is constantly changing. We're gonna scroll it down to all the points. Now the angle difference, which equals to distance PQ divided by the base. Scroll down. Why are we having... Oh, I'm sorry, I did not fix this. Now the angle rods is equal to A cosine base divided by radius. Yeah, I hope this is correct. Base circle, yeah, A cosine. Yeah, I have to fix this. Scroll it down. I think there's something weird. Let me just make this 30.08. Yeah, just a better reference. And now the angle, which is yeah, I'm a bit lazy today, so I'm just gonna copy this. 180 angle, this is equal to this, and this is equal to this. Did it work? Hope so. Yeah, correct. Now the angle HOP, which is the final thing, is equal to the base angle, which is this, and it's constant, plus the new angle that we added by moving our hand. as I showed you in the picture. Now the x-coordinates, simple. We know the angle, we know the constantly changing radius, so just that's what we're going to do. It's equal to the radius multiplied by sine the angle HOP. As it's constantly changing, radius multiplied by cosine angle HOP. Now, this so far so good. Now the dedundum. From where does the dedundum start? We know from the dedundum radius, as we calculated here the point A and point x coordinates of point A and x coordinates of point B. This is the this. Hope I put it correctly. Yeah. Hope I did it correctly. Think thing is that the y coordinates start from, I'm sorry, this should be here. The dedundum circle starts, oh yeah, because it's not the whole dedundum, it's this profile from G to A, and from since this starts from 2 point yeah, as I said, yeah, this also applies to here actually, so this equals to minus 2.2424 because we begin from A is equal to G, but it's the different angle since this is the y coordinate. So we move from negative to positive, and this gives us this shape of the involute that we are looking for. Yes, let's continue. Square root 3 this the dedundum, which we should fix, by the way. Oh, I should not have added this extra. Yeah, divide by minus the x value power 2. Correct? Yes. We're gonna make an increment here. About 2, and we're gonna keep doing till we get the 2.245 that we started with, but in the positive direction. What happened? I forgot to make it constant. Okay, we use this, and the addendum starts where the this stops, which is 5.6. As same as this, it starts with negative, and we move to the other axis, the opposite side, to the positive. I'm gonna choose the difference is 0.4. Yeah, this depends actually accuracy and your preference, honestly. 5.1, 5.5, 5.7, 5.71. This so I'm a bit lazy, as I said. This equals the same, but just change this and change from addendum to, sorry, addendum to addendum. Yeah, but why the extra one? Yeah, now we're gonna mirror the inputs, as now we have this, 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 but without this. We're gonna mirror the involute with just this coordinate, but just in negative. So we're gonna copy this, go here, go paste special, multiply. Oh yeah, sorry. Again, just paste it. Sorry, again. Paste values. Then we have -1 here. We're gonna go to -1, press copy, go to here. Hope I'm doing it correct. Paste special with multiply. Yeah, this is just a fancy way to doing it, because you can. Mirror is exactly the same values. Paste values. Now I'm gonna draw, or the draw, sorry. I'm gonna draw again the involute, this shape. Did we get it correctly or not? The between the teeth. Where was it? Sorry guys. Let's go. We're gonna choose scatter plot. I'm gonna choose the points at first, but I'm gonna, or should I not? Interesting. Select that. I'm gonna enter. The name is D done. The X values are right here. Oh my god, this is obstructing our work again. D done. Yeah, the X values. Here is the Y coordinates. Yeah, involute. It's right here. The Y coordinates of the involute. Add down. X coordinates. Y coordinates. Mirror involute. Yes, and this. Okay, we get this fine. Does not look really pretty, so I'm gonna make the minimum value here is 25. Will it become clear? How about 26? Yes. Just to make this clear, as we can see here, blue line is the dedenda. We have the involute right here, mirror involute, and the addendum on top, and this is the profile that we are looking for, and this is it. The next is using these 4 lines, which are from mirror involute, addendum to the actual involute, and we're going to implement this in SolidWorks. Now to continue from where we left off, we have, as I said, 4 curves. Now we need to extract the coordinates of these 4 curves. Get a new sheet. First of all, the involute. Copy here, go to another sheet, paste the values of it, and as we can see, here is the X, this is the X line, this is the Y line, and we need the Z line. I'm gonna make it 0. This is curve number 1. We need 3 axes to make it drawable in SolidWorks. We copy the dedendum, paste the values, add the Z axis. Done. Now the addendum, copy, paste values, and then add the Z axis, and we're gonna do the same for the mirroring videos, and the rest is about making it work. Just like as you can see, when we draw the figures, as we see here, like there is an uncertainty point, like it goes further to the right. Yeah, we need to fix these in SolidWorks. Okay, now we have the coordinates. Now I own a Mac, so I'm connecting TeamViewer to another Windows PC. We're gonna create a text file. Text document, we're gonna call it curve1 open, and we're gonna paste the first curve. Done. Save. Now next, we're gonna do the same thing for all the 4 curves, because this is how we're gonna implement it in SolidWorks. Control C, Control V. Next, curve number 3. Curve 3. So Control V. Yes, correct. Continue. Curve 4. The mirror involute. So copy, paste. Open up SolidWorks, and I have version 2019. Create a new part, and depends on your case, but I like to keep it centimeters. Go to insert, curve through XYZ points, browse where in our desktop, curve 1. Okay. As you can see here, we got the first curve. Now to continue the same process for each curve. Desktop, curve 3, desktop, now of course these curves will not be perfect, but we will correct them. Last curve, done. So let me check something. We need to know if is it a closed surface. No, because it's not shaded. This needs to be shaded so we know that it's a closed surface or not. If we zoom really closely, we can see that it's not connected. So we go here. Yeah, of course, there's another something I did not do. You first go here, and this is the front plane, right? Create a sketch, then offset entities. I'm sorry, I mean convert entities. This, because these are curves, are not part of a sketch. This, done. Just gonna hide those to better operate. As we can see, this curve is not closed, and we will work in that. I'm sorry, I'm using TeamViewer on my Mac, so control will be difficult. So let's go here, Done. Let's check this edge. Apologize for the movement. Okay. Now let's check the bot. As you can see, this is not closed. We have only one edge left. Is it closed? No, but as you can see, it's kind of weird. Done. As you can see, now it's shaded. And let's go to the front plane, create a new sketch. We have a circle that is the gear. Radius 36, which is the same radius as our gear. We're gonna exit sketch, evaluate, or feature, so extrude. Let's say 10 centimeters. Blind. Okay. And then we go to this sketch. Extrude cut. Blind. Let me get through all. Flip the direction. Make direction to through all, yeah. Here we have created the profile between the two teeth. Now we go to insert. Oh, I'm sorry, linear pattern. Go here. We have circular pattern. But before we do that, we need this is the right plane. Create a sketch. Let's make a line. And now we can make it linear, circular, 360, the features and faces. How many tooths do we have? Uh, 16. Something is wrong, I don't know what it is. Oh yeah, I did not do the angle correctly. Since we have 360 angle divided by 16, the 22.5 will it be? Done. And by this we have created our gear in the most hopefully correct way possible. This is it. Thank you for watching, and I will link my research in the description so you can check it out on my Researcher's Gate profile. I hopefully this video was instructive and helped you to create your gear. And this is the most accurate way. This is why I did this research. I think I found it the most accurate way of doing it. Again, thank you very much, and good luck on your journey to acquire the knowledge. or knowledge in. Thank you.